Hello, my precious friends. I really hope that you are doing great. Welcome to our today's class. It's our second lesson on the sixth topic of Form 3 work, which is called Waves 2. As usual, let me commence by giving you the quote of the day, which states that sometimes you need bad situations to happen in your life in order for you to change and grow. We shall discuss that quote at the end of our class today. So today we are looking at refraction of waves. So maybe to understand it better, you can just review our second chapter of Form 3 work, which was called Refraction of Light. That is to understand this part better. So under that chapter, which was our chapter 2 of Form 3 work, we did say that refraction simply refers to the bending of light at the interface when it travels from one medium to another at an angle. Now for that case we were only discussing refraction of light, but for this case we are talking of refraction of different types of waves. For example, we can have the water waves, we can have the light wave, we can have the sound wave, etc. So refraction occurs when the waves move from one medium to another of different densities. So for there to be the bending of a wave, the two medium must have different densities. So first of all, let's start by looking at refraction in water waves. So in water waves, refraction, which involves simply change of medium, occurs when the water waves move from shallow to deep regions and vice versa. So water can also be moving from deep regions to the shallow region. So in that case, there will be change of medium. That is, the density of the water in the deep region will be slightly different with the density of the water in shallow regions. That's why we are talking of the change of medium, that is from deep to shallow waters or from shallow to deep waters. So to understand that better, let's start by looking at a scenario whereby we have the wavefronts being parallel to the boundary or to the interface. So consider this particular wave here, this transverse wave, which is traveling from the left hand side towards the right hand side of this particular page. So if a wave is traveling towards the right hand side, then you can see this particular wave is actually perpendicular to our interface or perpendicular to our boundary. So whenever we have wavefronts being parallel to the boundary, such as the ones that we have here, it simply means that the wave is actually, the direction of the wave travel is perpendicular to the boundary or to the interface. So you can clearly see that this particular transverse wave is moving towards the right hand direction, and the direction of its motion is represented by this particular line here. So because this line is traveling towards the right hand direction and our interface is actually perpendicular, or our boundary is perpendicular to the direction of wave motion, you can clearly see that our wavefronts are also perpendicular to the direction of wave motion. So whenever we talk of wavefronts being parallel to the boundary, we simply mean that the direction of wave travel is perpendicular to the boundary. Or if the wavefronts are parallel to the boundary, it simply means the direction of wave motion is perpendicular to the boundary. Therefore, we are saying that for the water waves, the change of medium will involve moving from deep to shallow region or from shallow to deep region. So the most important thing to note here, we want to consider a case scenario whereby we have a wave which is, or the light wave, which is traveling from one medium to another. Remember from refraction of light, that is our first lesson on refraction of light, which was our second, that is our topic 2 of Form 3 work. You can just review. We did say that whenever you have that, whenever a ray travels perpendicular to the interface or to the boundary such that the angle of incidence is 0, then such a ray continues in a straight line since there is no change in direction. So remember, if the incident ray is perpendicular to the boundary, it simply means that the incident ray is actually perpendicular, or it is the incident ray is actually parallel to our normal. So when the incident ray is parallel to the normal, such a wave will continue in a straight line, or it will pass undeviated. Its direction of motion will not change. So it is actually the same thing that is happening here. So you can see the direction of our wave motion is actually perpendicular to our boundary. You can see the angle between our boundary and the line which is representing the direction of our wave motion, this angle is actually 90 degrees. So in short, this particular direction of wave motion is parallel to the normal. It is parallel to the normal. So this line is parallel to the normal, simply meaning that this particular line, or which is representing the direction of our wave motion, is perpendicular to the boundary. Then whenever you have a wave being perpendicular to the boundary or to the interface, it simply means such a wave will not be deviated. Instead, it will continue traveling in a straight path, that is in undeviated manner, because the angle of incidence is actually 0, simply because the incident ray is perpendicular, or is the incident ray is actually parallel to our normal. So for this case, this incident wave, we expect it to continue undeviated because it is actually meeting our boundary at an angle of 90 degrees, and therefore it is the direction of motion of our incident wave is actually parallel to the normal. It is parallel to the normal. So the key thing to note here is actually the distance between the successive wave fronts. And remember from our previous class, we also said that the distance between any two successive wave fronts will always be equal to the wavelength, such as the one shown here. The distance between successive wave fronts will always be equal to the wavelength of that particular wave. So when the wave is traveling, when the water wave is traveling through deep water regions, the distance between any two successive wave fronts is usually large, or the wave fronts are usually widely spaced. But when the water wave is traveling through shallow water regions, the wave fronts are always closer to one another. And because we are saying that the distance between any two successive wave fronts is equal to the wavelength, it simply follows that the wavelength of a wave when traveling over the water wave, when traveling in deep water regions, will always be larger. And remember from waves 1, we did say that velocity of a wave is equal to the product of its frequency and the wavelength. So from this formula, it can be deduced that the velocity of the wave is directly proportional to the wavelength. That is, if we hold frequency constant. So at constant frequency, the velocity of a wave will always be directly proportional to the wavelength of that particular wave. So that simply means that the higher the wavelength, the higher the velocity of the wave. And the smaller the wavelength, the lower the speed or the velocity of the wave. So for this case, because our wavelength is large, or the distance between successive wavefronts is large, that is in deep water regions, it simply means that in this particular region, the speed or the velocity of the wave in deep water region will always be very, very high. So I can give you a case scenario here. Suppose the wave was moving at a constant frequency of 2 Hz. Then for this case, the velocity of the wave in the deep water region will be given by the frequency, which is 2 Hz, times the wavelength. So you can see the wavelength in this case is 10 meters because it is larger. So the velocity of the wave in the deep water region will actually be 2 times 10, which gives us a velocity of 20 meters per second. However, we also consider another case scenario whereby the same wave, it is moving at the same frequency of 2 Hz, but now for this case, in shallow water regions, the wave fronts are closer to each other, meaning that the wavelength will be smaller, because we know that the distance between any two successive wavefronts will always be equal to the wavelength. So if the wavelength is smaller, for example, in this case, a wavelength of 2, that is 2 meters, it simply means that the velocity for this case will be equal to the frequency, which is a constant 2, times the wavelength, which is 2. So you can see for this case, the speed is 4 meters per second. So if you compare the speed of 4 meters per second and the speed of 20 meters per second, you can clearly see that the speed of the water wave in deep water regions is higher. That is, it is 20 meters per second, but for the shallow water regions, it is only 4 meters per second. So you can easily conclude that the speed of the water wave in deep water regions will always be very high as compared to the speed of the water wave in shallow water regions. So the shallow water regions, the speed of the water wave will be very low speed, but in deep water regions, the speed of the water wave will be very, very high. We have said the reason is because in deep water regions, the water will always, or the wave will always move in such a way that the distance between successive wave fronts are always larger. Therefore, if the distance between successive wave fronts are larger, it simply means that the wavelength is also larger in deep water regions. And you have seen that the velocity of the wave in water regions is directly proportional to the wavelength. Therefore, the larger the wavelength, the higher the speed of the water. And of course, the smaller the wavelength, the lower the speed of the water. So maybe in an exam scenario, you will just be given the incident wavefronts, then you will be asked to sketch or to show how the wavefronts will move in shallow water regions. So the key thing here to notice that in shallow water regions, the wavefronts will always be closer to one another, such as the ones drawn in purple color in this case. But the wavefronts in deep water regions will always be largely spaced, or they will always have huge spaces in between them. So that is the key point to note there. Remember, you can also be given a question whereby you are given maybe the wave moving from shallow water regions to deep water regions. So in that case, just remember that when the wave moved towards the deep water regions, remember that the spacing between the wave fronts should be larger, indicating that the wave, that is the wavelength, is larger, and therefore also the speed of the wave is also larger. Then Roman 2, we want to look at a case scenario whereby we have wavefronts meeting the boundary at an angle. Now in this case, it simply means that we can compare it with a situation whereby we have a ray that is an incident ray having an angle of incident I. So in such a case, the wave will be refracted in such a way that it bends towards the normal. So you can see this is our angle of refraction. So similarly, for the water waves can also be refracted. But refraction can only take place if the incident wave is not meeting our boundary at an angle of 90. For example, in this case, you can see our boundary is somehow twisted, and the wave fronts are actually parallel, or they are they are parallel to each other, or they are vertical. So because they are meeting our boundary at some angle, an angle I, so the angle of incidence is actually not 90 degrees. So that angle is also not 0 degrees. So it is meeting it at some angle, let's say maybe an angle of 30 degrees. So if it meets it at an angle of 30 degrees, upon reaching the boundary, that particular incident wave, that is the water wave, will be refracted. So remember, to refract simply means to bend. So you can see our incident water wave is being bent at this particular boundary or at the interface. So the wave will bend downwards, or in such a way that it approaches our normal. Then the key thing also to notice that the distance between successive wave fronts. For deep water region, the distance between successive wave fronts has to be larger, showing that the speed of the wave is higher, as we have shown in this particular equation. And for shallow water region, the wave fronts should be closer to one another, simply showing that the wavelength for the shallow water regions, the wavelength of the water waves will be very small, showing that the speed of the water wave in shallow water regions will also be very, very low. Next, we look at refraction of plane or straight water waves on a curved surface. So remember, from waves 1, that is from waves 2 lesson 1, we did say that for the plane waves, which are incident, they always be reflected or refracted in such a way that they take the refracted wave will always take the shape of the refracting surface. And for this case, we are talking of a curved surface. So this particular curved surface is our refracting surface. So you can see that the refracted waves are also curved. That is, they are taking the shape of the refracting surface. Then, of course, if the incident wave was moving towards the right, the refracted wave will also be moving towards the same direction. Then number 2, we look at refraction in sound waves. Then we are saying that during the day, sound from distant sources. Remember, distant sources, these are sources that are very far away from us. So during the day, sound from distant sources are usually soft or not clear, since the waves are refracted upward from the hot earth. So remember, during daytime, and especially when we have the sun, so the land usually absorbs radiant heat from the sun. So when it absorbs the radiant heat from the sun, it also heats the air which is around that particular land. So when air is heated, of course, its temperature will increase. Then from particulate nature of matter, we did say that the kinetic theory of matter stated that whenever whenever air is heated or whenever temperature is increased, that will simply mean that also the speed or the velocity at which that particular air will be moving will be very high. So because of the increased temperature, the hot air will be moving at a very, very high speed. Therefore, the wave fronts in the hot air will also be moving at a faster rate. And conversely, the air that is above that particular ground, or the air that is far away from the land, of course, it will be cooler as compared to the air near the ground, because the air that is near the ground is the one that has been heated by the heat that was absorbed from the sun. So the air that is above the ground is very cool, and therefore, for cool air has a very low temperature, and therefore the speed of motion of the wave fronts will also be very, very low. Now we are ending up with a situation whereby the wave fronts near the ground are moving at a very faster rate because of the increased temperature, but the wave fronts above, that are far away from the ground, are moving at a low speed because of the low temperature. So because of the difference in the speeds of the wave fronts, we'll end up with this particular scenario. So consider, I want you to imagine being in a car which is having the front wheels. So if one of the wheels is moving at a very high speed of 10 meters per second and the other wheel is moving at a very low speed of 3 meters per second, you will notice that that car will always rotate in such a way that it moves in the direction of the wheel that is moving at a very, very low speed. So the same scenario happens here. The air or the wave fronts that are in the hot air which is near the ground are moving at a very faster speed, that is at a higher speed. But the wave fronts that are far away from the ground, that is in the cool air, are moving at a very, very low speed because of their low temperature. So obviously, just like this particular car, the sound that is produced from our speaker, it will be refracted upwards, or it will be refracted away from the ground. Therefore, the observer who is at this particular point will not be able to hear the sound that was produced from the speaker. But yeah, so this explains why during daytime the sound is produced, yes, but it cannot travel to longer distances, because the people who are, for example, at this particular point will not get any sound, because all the sound is refracted upward. It is refracted upward. However, at night, the land usually cools at a faster rate. Remember, we also explained these in Form 1, that is when we were looking at the land and sea breezes. So at night, the land usually cools very fast. So the sound from distant sources, that is the sources which are very far from us, are usually louder since sound is refracted downwards, that is to the cooling land. So at night, the heat that was absorbed by the land, it will be lost. So as the heat gets lost, that means the air that is near the land will also be very cold, or it will cool. Then we know that cold air has a very low temperature, and when the temperature is low, from the kinetic theory of matter, the molecules will also be moving at a very slow speed, because they do not have the kinetic energy which can make them to move faster. So when the air molecules are moving slower, it means that the wave fronts of the air near the ground are also moving at a very, very low speed. But the lost heat, remember, the heat is being lost to the atmosphere. So that means the air that is above, or the air that is in the atmosphere, or the air that is very far much beyond the ground, is actually warm, because it has gained the heat that was lost by the land. So when the air is warm, its temperature, of course, is very high. The higher the temperature, the more the kinetic energy of the molecules. So when molecules have more kinetic energy, it means they can easily move from one region to another. Therefore, the speed of the wave fronts, that is for the air that, or for the warm air that is above that particular ground, its speed will be higher, because that particular air is now at a higher temperature. Therefore, it has more kinetic energy to move. So when the wave fronts are moving at a very high speed, it simply means that the wave at this particular upper ground will also travel at a very high speed. So you'll end up with a scenario whereby you have, for example, let's go back to the wheels of our car. So you have one wheel moving at a higher speed of 10 meters per second. The other wheel is moving at a very low speed of 10 meters per second, but attached on the same vehicle. So in such a scenario, the vehicle will always move in the direction of the wheel that has a very low speed, that is of 3 meters per second. So same case here, the lower air or the cool air, the wave fronts are moving at a very low speed, but the wavefronts that are on the upper side are moving at a very high speed. So just like this vehicle, which will turn in the direction of the vehicle that is the wheel that is moving at a lower speed, also the sound wave that is produced from this particular speaker, that is at night, it will always be refracted downwards, or it will bend downwards. So it will be refracted downwards in the direction of the wavefronts that are moving at a lower speed. Just like for this case, where the vehicle is also turning in the direction of the wheel that is moving at a very, very low speed. So this explains why you are able to hear sound from very distant sources, usually at night, because an observer at this particular point, which is a point far away from the speaker or the source of sound, is able to hear the sound very clearly, because sound is refracted downwards, that is at night. So in brief, you have just said that for this particular case, during daytime, the heat from the sun is usually absorbed by the land, causing the air near the land to be hot, or to increasing the temperature of the air near the land. So when the temperature of the air increases, of course, the air will move at a faster rate, causing the wavefronts near the land to also move at a faster rate. As the wavefronts move at a faster rate, the air above the ground, that is far away from the ground, is cool, and of course its temperature is low, hence the speed of the wavefronts in the cool air is also low. So this causes the sound to be refracted upward, hence not to longer distances. But at night, the heat that is the land usually cools at a faster rate, causing the air near it to also cool. So when the temperature of the air near the ground is low, that means the wavefronts will be moving at a lower speed, because the kinetic energy in the air is also low. However, the air that is above the ground is now warm, because it has gained the heat that was lost from the ground. When air is warm, it means its temperature is high, therefore the kinetic energy of the air is also high. When the air has a lot of kinetic energy, it is able to move at a faster rate. Therefore, the wavefronts at the higher ground is moving at a faster rate. Therefore, the wave or the sound wave from the speaker will be refracted downwards. Yeah, so just try listening at night. When sound is from a very far or a distant source or a loudspeaker, you are able to hear that particular sound very clearly, as if it was closer to you. But during daytime, the sound that is produced far away from you, you will not be in a position to hear that particular sound, because it is refracted upwards. Next, having looked at the two properties of waves, that is reflection and refraction, let's look at the third property of waves, which is called diffraction of waves. So diffraction simply refers to the spreading out of waves when it strikes an obstacle or a slit. A slit is just a gap or an opening or an aperture, yeah, or just some spaces. Then the extent of diffraction depends on two factors: one, the wavelength of the wave, and two, the size of the slit or the size of the gap. So you can be asked to give two factors affecting the extent of diffraction, or affecting the diffraction of a wave. So the answer will be one, the wavelength of the wave, and two, the size of the slit or the size of the gap or the size of the aperture. An aperture is just an opening. Then sound waves are usually more readily diffracted than light waves, because sound waves, the sound waves have a longer wavelength. Yeah. For example, if my sound is able to move outside the wall of my house, but the light may not be in a position to move outside the wall of the light, because the light cannot travel in a path that is not straight, but actually sound can actually be diffracted, or it can spread beyond a straight path. So sound waves are usually more diffracted than light waves, because sound waves have a longer wavelength. So that is the reason. So actually, the longer the wavelength or the larger the wavelength, the more the diffraction, and the smaller the wavelength, the lesser the amount of diffraction. So this makes it possible to hear sound around obstacles. Yeah, sound can actually move beyond walls, but light cannot move beyond a wall, because it must obey the rectilinear propagation. Then the way in which the size of the slit affects diffraction is usually that the smaller the gap or the smaller the slit, the higher the rate of diffraction. For example, we can look at this particular case. you can see that our slit or the gap is small, and it is smaller than the wavelength. So the wavelength is larger, which is 3 centimeters, but the gap or the slit is small, which is 1 centimeter. So the smaller the gap, the faster or the larger the rate of diffraction. So you can see that for this particular wave, these incident waves have been diffracted more. That is, they are spreading more. So the smaller the gap or the smaller the slit, the higher the rate of diffraction. However, for this case, for the case of wavelength, the larger the wavelength, the smaller the rate of diffraction. So in this case, you can see the wavelength is 3 centimeters, but the gap or the slit is larger, which is 7 centimeters. So the smaller the wavelength, the smaller the rate of diffraction. For this case, you can see that the diffracted waves, the rate of diffraction is actually small because the waves have not spread into a wider space as compared to this particular case. Remember, we have said that diffraction is the spreading out of waves. Therefore, the smaller the spreading, the smaller or the lower the rate of diffraction. But the more the spread the waves are, the higher the rate of diffraction. So whenever the slit is very small, the diffraction will be very high, or the spreading of the wave. But whenever the slit is very higher than the wavelength, then the rate of diffraction will also be very, very small. So in an exam situation, you'll be given incident waves, then you'll be asked to sketch the diffracted waves, in one case when the slit is small, and the other case when the slit is larger. The other case will be given, that is, they will be comparing the wavelength. So in one case you are given when the wavelength is smaller than the slit, then the other case you are given when the wavelength is larger than the slit. So you should be in a position to sketch the rate of diffraction. Just remember that the smaller the slit, the faster the rate of diffraction. The larger the slit, the smaller the rate of diffraction. Then the larger the wavelength, the larger the wavelength, the smaller the rate of diffraction. No, the larger the wavelength, the faster the rate of diffraction. Yeah, when the wavelength is long, the diffraction is also very large. But when the wavelength is very small, the diffraction also becomes very small. So that simply explains the reason why diffraction in sound waves is faster than in light wave, because sound waves have usually longer wavelength as compared to the light waves. Another person maybe will ask you to give a reason why diffraction in light waves is smaller than in sound waves. So the reason will be because the light waves have a smaller wavelength as compared to the sound waves. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that sometimes you need bad situations to happen in your life in order for you to change and grow. So the quote is just reminding us that not every challenge we face comes with an intention of destroying us. Actually, most of the challenges that we face in our lives are usually a blessing in disguise, because those challenges are usually accompanied by lessons which are very essential for our future growth and for our future development. Therefore, we should embrace the challenges instead of running away from them, and we should be in a position to extract the lessons that those challenges intended to teach us. For instance, for you to fully understand the importance of conserving water, you must first live in a desert, that is, in a region where accessibility of water is a challenge. So when you are able to live in an area where water is a challenge, you will be able to appreciate the importance of conserving water. And lastly, recall that the biggest lesson in life, the biggest lessons that you will learn in life are usually learned after overcoming an adversity or a challenging moment. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. If you also know any student that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy, or just share my link to them. This is Kind Tuition Academy. Until next time.